Good afternoon, sir. Myself Noori Sumaya from CSA department. Today my topic for the presentation is extrinsic semiconductors P and N type. In this slide, let us know about brief introduction of semiconductors. Semiconductors are the materials whose conductivity lies between conductance and insulators, or semiconductors are the materials which allows current partially to pass through it. They are widely used in electronic devices due to their ability to control electrical properties. Extrinsic semiconductors are formed by doping uh, pure impurities to improve their conductivity. Unlike intrinsic semiconductors, which rely on temperature for charge carrier generation, extrinsic semiconductors achieve higher conductivity through doping. There are two types of extrinsic semiconductors, p-type and n-type. N-type semiconductors are formed by doping pentavalent impurities, for example, phosphorus, arsenic, pure silicon, or germanium. N-type semiconductor introduces extra free electrons, making electrons the majority charge carriers and the holes are minority charge carriers. P-type semiconductors. P-type semiconductor is formed by doping trivalent impurities, for example, boron or aluminum. It creates additional holes, making hole the majority charge carriers and electrons are the minority charge carriers. In this slide, let us know about N-type semiconductor. An N-type semiconductor is a type of extrinsic semiconductor in which the majority charge carriers are electrons and the minority are holes. It is created by doping a pure semiconductor such as silicon or germanium with a small amount of pentavalent elements such as arsenic, antimony, or phosphorus. The key characteristics of N-type semiconductor are doping elements, pentavalent elements, which have 5 valence electrons like phosphorus, arsenic, or antimony. The majority charge carriers are electrons, nothing but negative charge. The minority charge carriers are holes, which are positive charge. The conductivity is increased due to the extra free electrons contributed by doping atoms. The electric field behavior. Electron moves towards the positive terminal when a voltage is applied. The donor energy level is close to the conduction band, making it easier for electrons to jump and contribute in the conduction. In this slide, let us know about properties of N-type semiconductor. N-type semiconductors are materials that have been doped with elements that introduces an excess of electrons, making them more conductive. Here are the key properties of N-type semiconductors. They have majority charge carriers, and minority charge carriers are holes and the majority charge carriers are electrons. Doping elements typically doped with pentavalent elements arsenic, antimony and phosphorus. Conductivity N-type semiconductor has higher electrical conductivity than intrinsic semiconductor due to the availability of free electrons. Direction of current flow. Electrons move from the negative to the positive terminal when external voltage is applied. Fermi level. The Fermi level is closer to the conduction band and in a N-type semiconductor. The conduction occurs primarily due to the movement of free electrons. Response to electric field. Under an electric field, electrons move forward to the positive terminal and the current flow easily. Energy band diagram. The conduction band has more electrons compared to the intrinsic semiconductors. Thermal behavior. As temperature increases, more electrons gain through energy to jump into the conduction band, increasing conductivity. Here are some pictures related to p-type and n-type semiconductors. P-type semiconductors are defined as a type of extrinsic semiconductors that has been doped with a group 3 elements, nothing but trivalent elements such as boron, resulting in an excess of holes, positive charge carriers. They are positive charge carriers. Characteristics of P-type semiconductors are the majority charge carriers are holes, nothing but positive charge carriers, and the minority charge carriers are electrons. Group 3 elements, nothing but trivalent impurities, are doped into the p-type semiconductors to improve their conductivity. The conductivity is increased due to excess holes. The Fermi level is shifted closer to the valence band. The p-type semiconductors are formed by doping a pure semiconductor materials with a group 3 elements, nothing but trivalent impurities. The dopant atoms replace the sum of the silicon atoms in the lattice, resulting in the excess of holes. Here are the properties of p-type semiconductors. P-type semiconductors exhibits a positive Hall coefficient indicating that the majority charge carriers or holes, the increased hole density. P-type semiconductors have a higher hole density than electron density. Shifted Fermi level. The Fermi level in P-type semiconductors is shifted closer to the valence band, indicating an increase in hole concentration. Acceptor impurity levels. P-type semiconductors have acceptor impurity levels near to the valence band with accept electrons and creates holes. Anisotropic conductivity. P-type semiconductors can exhibit anisotropic conductivity due to the orientation of crystal lattice. Applications of extrinsic semiconductors. Extrinsic semiconductors are used in particle detectors such as silicon detectors to detect and track charged particles. Semiconductors are used in radiation detection instruments such as Geiger counters to detect and measure ionizing radiation. Semiconductors are used in thermistors, which are temperature sensing devices used in temperature measurement and control. Extrinsic semiconductors are used in Hall effect sensors, which measures magnetic field and are used in applications such as position sensing and current measurement. Extrinsic semiconductors are used in optical communication systems such as photodetectors and optical amplifiers. I end my presentation here. Thank you.